Hamiltonian cycles. A cycle in a graph is a closed walk that does not touch any vertex twice, except of course the initial vertex that must also be the ending vertex. This implies that if a cycle has k vertices, then it has k edges. A cycle that includes all vertices of a graph is called a Hamiltonian cycle, whereas a path that includes all vertices of a graph is called a Hamiltonian path. A real-life scenario in which Hamiltonian cycles are relevant is the following. Suppose many people are invited to a party and they will all be seated around a circular table. Is it possible to find seating arrangements so that each guest knows both people seated next to him? In this scenario, we can define a graph in which people are represented by vertices and two vertices are connected by an edge if the corresponding people know each other. Then a Hamiltonian cycle in this graph, if it exists, provides an appropriate seating. Whether a Hamiltonian cycle exists in this graph depends, of course, on the graph itself. For example, if there is a person who does not know anyone, then it is clear that there is no Hamiltonian cycle. If there is no such a person, but the graph is not connected, then there will not be a Hamiltonian cycle either. If everyone knows everyone, then of course there will be a Hamiltonian cycle. These were all very special situations. What can be said about the general case, though? That is, given a simple graph G, how can we quickly decide whether it has a Hamiltonian cycle or not? The answer to this question is that we cannot. It is easy to prove that an appropriate seating exists when it exists. Indeed, you can prove that by simply exhibiting one. There is, however, no quick way known to prove that no appropriate seating exists when it does not. By quick way, we mean an algorithm that uses only f of n steps, where n is the number of guests, and f of n is a polynomial function of n, such as n cubed, or n to the 7th plus 3 times n to the 5th plus 6n plus 3. We can certainly prove that no good seating exists by verifying all n minus 1 factorial possible seating arrangements and concluding that none of them are good. But that takes too long. The function g of n is equal to n minus 1 factorial is not a polynomial function of n. This problem is interesting on its own, but it is also related to a vast array of very important problems of an exciting area in theoretical computer science called complexity theory, which is the topic of chapter 18 of this book. So it is well worth reading the book till the very end. It can be proved that the problem of deciding whether a given simple graph has a Hamiltonian cycle is equivalent to about 5,000 other problems which are all very different at first sight. By equivalent, we mean that if a polynomial time algorithm were found for the Hamiltonian cycle problem, then that would provide a polynomial time algorithm for any of those 5,000 problems, and vice versa. The set of all these equivalent problems is called NP-complete problems. It is a belief that by most, but not all researchers, that such polynomial time algorithm does not exist. You can try to find one, but do not try too hard. There are nevertheless some non-trivial theorems about the existence of Hamiltonian cycles. Theorem 9.5, let G be a simple graph on n vertices and assume that all vertices in G are of degree at least n over 2. Then, G has a Hamiltonian cycle. Proof. Let us assume that G does not have a Hamiltonian cycle. Let us add new edges to G as long as we can without creating a Hamiltonian cycle. When we stop, we have a graph G prime in which all vertices have degree at least n minus and over 2, there is no Hamiltonian cycle, but adding any new h would create a Hamiltonian cycle. Let x and y be the two vertices in G' that are not connected by an h, as adding the hxy would create a Hamiltonian cycle. It follows that G' has a Hamiltonian path P that starts at x and ends in y. Denote x equals to z1, z2, z3 until zn minus 1 and zn is equals to y. That is, z1 is the start of the Hamiltonian path, and which is also labeled with x, and zn is labeled with y, which is also the end of the Hamiltonian path. The vertices of this path from x to y, vertices x and y together, have at least n neighbors. Therefore, the pigeonhole principle implies that there must be an index I, so that I which is between 2 and n minus 1, where x, z, I is an h, and also z, I minus 1, y is an h. This is a contradiction. However, for this would mean that x, z2, z3, z4, z, I minus 1, y, z, n minus 1, z, n minus 2, and so on until zi is a Hamiltonian cycle, as shown in figure. There are several additional results proving that a simple graph in which the degrees are, in some sense, large has a Hamiltonian cycle. We will see some of these results in the exercises.